All right, so let's talk about writing net ionic equations. The first thing you need to have handy is your solubility rules, right? You can't do this without solubility rules. And there are 3 steps. First, you write the molecular equation. Write a balanced molecular equation and look for a precipitate, PPT for short. What's the precipitate? What is a precipitate? It's the product that has what state of matter after it? Solid, right? It's the solid. Is there always a precipitate though? No, not always. So look for a precipitate using your solubility rules. Then you're going to write a balanced, complete ionic equation. So how do we do that? We dissociate everything but your precipitate or a gas if you have gases in there. And don't forget charges. That's the #1 mistake I see, right? Ion, think ionic, right? If it's an ionic equation, it has to have charges. Ag and Ag plus are not the same thing, right? So do not forget your charges. Then you would cross out your spectators. And that gives you net ionic. Now, what's the scenario called where there is not a precipitate? If there is no precipitate. Right, NAR. That stands for no apparent reaction. If there's no precipitate, then nothing's actually happening, right? You're just taking a mixture, and you're taking another mixture, and you're combining them, and you're making a third mixture, but nothing chemically is taking place, right? So if there's no precipitate, you can just write your balanced molecular equation, show that both products are soluble, and then stop, and then you can just write NAR. And then as your explanation, you would just say because both products are soluble. So that's the ideal situation in terms of not having to write much, right? Because if both your products are soluble, then there's nothing chemically that took place. You just physically combine some ions. All right, so those are the steps in writing net ionic equations. So let's go through an example. Why is my camera not focusing? It's kind of driving me crazy. It's focused on my hand. Now focus out here. Come on, that's better. All right, let's go through an example or two. Let's do barium nitrate plus sodium hydroxide. Barium nitrate and sodium hydroxide solutions are mixed, and we want to know what's the net ionic equation, if there is one. Because does no apparent reaction have a net ionic equation? No, because nothing's happening, right? So first we need to figure out, is it no apparent reaction or is something actually taking place? So let's write our formula. What's the formula for barium ion? Barium ion has what charge? 2+. And what's nitrate? NO3 minus. So when they get together, that would be Ba. Crisscross those. Right. NO3, 2. And it's aqueous because that's my reactant, right? That's a reactant. So I don't have to worry about looking up its solubility because it's a reactant. And sodium hydroxide, what's sodium's charge as an ion? 1. Na+. And what's hydroxide? OH minus. So we crisscross those, that's just a 1-to-1 ratio, right? So that's just NaOH. There we go, we finally got in focus there. Okay, this is a double displacement reaction, right? So that means the cation from here gets together with the anion from here, and the cation from here gets together with the anion from here. So when I combine the products, I'm going to have barium ion and hydroxide ion. So when I crisscross those, is this the correct formula for barium hydroxide? I see this all the time. Is that the correct formula for barium hydroxide? No, what's wrong with that? It needs parentheses, right? Polyatomic ions always need parentheses around them. Now look at your solubility rules. Is this one soluble or insoluble? I'm going to pull mine up on my screen here. Hydroxide ion, let's see, on our handout, that would be number 10. Ionic compounds containing the following are generally insoluble. Hydroxide ion. But is barium listed as one of those exceptions that is soluble? Yes. So would barium hydroxide be AQ or S? AQ. And now let's figure out our other product. Sodium ion and nitrate ion. So that's Na plus and NO3 minus. Am I still on the screen? Yes, I am. So when you write those together, that's just NaNO3. Okay, look at your handouts. For nitrate ion, are there any exceptions to solubility of nitrate? Nope, everything's soluble in nitrate. So that's AQ as well. And now we just need to balance this. So we need 2 NaOH and we need 2 NaNO3. So that's the molecular. Okay, what can we go from here? Is there a precipitate? No, there's no precipitate. So what will we call this? No apparent reaction, NAR, right? You can stop right here and just say no apparent reaction because both products are soluble. Okay? You can stop right there and you don't have to do anything else. Because if you try to write a net ionic equation, you dissociate this, you dissociate this, you dissociate this, you dissociate this. What's going to happen when you, so all going to cancel out, right? You'll be left with nothing. You're literally going to cross everything out. So why waste your time writing all that out, right? If nothing's happening, you're just making a mixture. That's all there is to it. No apparent reaction. Do we see how to do this kind of problem? There was no apparent reaction on the handout that you did for homework. So when you see the answer key, that's what I write for the answer, and I would accept that as an answer from you as well. As long as you put because both products are soluble, right? I want the justification. Any questions on this one? All right, let's do one. Let's keep barium nitrate, but this time, let's see. Let's pick sodium phosphate. Pretty sure that one's insoluble. Yeah, let's see. Yep, that one will be insoluble. So we already have revealed the answer. So let's look at the net ionic equation. All right, so barium nitrate is still BaNO3, 2. Sodium ion is still Na plus. What's phosphate? PO4 3 minus, right? So when we crisscross those, we get Na3PO4. So BaNO3, 2 aqueous plus Na3PO4 aqueous. We're going to crisscross, right? So that means our products are going to be barium phosphate. So barium ion is Ba2 plus, phosphate is PO4 3 minus. So when we crisscross those, we're going to get Ba3 PO4 2. What's that? Soluble or insoluble? That will be insoluble. So what subscript does it get? solid. And then our other product will be sodium nitrate. So Na plus, NO3 minus. So that's NaNO3, and that's aqueous. All right, now let's go through and balance this. Let's see, we need what? We need a 3Ba, and we need a 2 here, and then we need a 6 here. All right, there's our molecular equation. We do have a precipitate this time. All right, that's the molecular equation. Now we need to write the complete ionic. Move that out of the way. Complete ionic. So when we do a complete ionic equation, we have to dissociate everything that is not a solid or a gas. We didn't form any gases here, so who cares? All right, now this 3 gets distributed across the whole thing. So when this dissociates, you've got 3 Ba2 plus Aq, right? Don't forget the charges, because this is made out of barium ion, not barium metal, right? So when it dissociates, it's dissociating into barium ion, not barium metal, okay? Now, 3 times how many nitrates are here? 2, so 3 times 2, that would be 6. Never, ever, 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 ever split up a polyatomic ion. Okay, I always know someone who doesn't know what they're doing if they start splitting up a polyatomic ion. Polyatomic ions are units, they stay together. So when I'm grading tests or quizzes or something and I see polyatomic ions being split up, I'm like, oh, you didn't know what you're doing, right? Because polyatomic ion always stays together. There are 3, there's a coefficient of 3, there are 2 nitrates in the compound, so that's where that 6 comes from. Is everybody with me on how we got that? Same thing's going to happen here. There's a coefficient of 2, but there are 3 sodium ions, so that's 6 Na plus, and then 2 times 1 is 2, 2PO4 3 minus. We're going to leave the precipitate alone. Leave it alone, just write it directly the same. And then distribute this 6. 6 Na plus 6 NO3 minus. I know it's a lot of little details, but make sure you put all your charges, make sure you put all your subscripts, okay? This does matter what state this is, okay? So make sure you put that. Now, when you're crossing out your spectators, they should match exactly. For something on both sides of the equation, they should match exactly. And if they don't match exactly, then you know you made a mistake somewhere. You go back and double check your translation from here to here. What are the spectators in this equation? There are 2. What are they? Yep, they are. 6 Na plus, 6 Na plus, 6 NO3 minus, 6 NO3 minus. So what you're left with is what's actually taking place. So a spectator is just floating around in your solution. It's not actually doing anything, right? Just like if you go watch a basketball game, right? You're not on the court playing, you're just watching, you're a spectator. Same thing's happening in your solution. The sodium ion and the nitrate ion are just floating around. They're not doing anything, they're just hanging out. What's actually taking place is represented by the net ionic equation. Net ionic is what you're left with. So 3Ba2 plus 2PO4 3 minus formed Ba3PO4 2 solid. And that's what's actually taking place. And if you did it correctly, your net ionic equation should already be balanced for you. Because if your molecular was balanced, and then you translated it into complete ionic correctly, then when you cross out your spectators, your net ionic should already be balanced. You shouldn't have to balance it, because it should already be fixed. So do we see how to do no apparent reaction versus one that involves a precipitate? Yes. Any questions on how to do this? All right, so now we're gonna switch gears and we're gonna start talking about acids and bases, which is based on net ionic equations. So if you don't have your calculator out, go ahead and pull it out. All right. So let's talk about common acids. And this is intro chem, so intro to common acids. What are some general properties of acids? They have a pH less than 7. Right, their pHs are less than 7. They have a sour taste. Right, so think of some things that taste sour. Lemon juice, right? That tastes sour. Lime juice. All of those kinds of things that have a sour taste to it. Sour candies, all that stuff. All come from those acid components. They corrode many metals. Those are some general properties of acids. And then how do we name acids? In intro chem, you only have to name 2 types of acids. If you take general chem, I'll teach you how to learn 3 types of acids. But in intro chem, you'll have to do 2 types. So naming. So we've got type 1 and type 2. In Gen Chem, if you take General Chem, there'll be 3 types you learn, but in Intro Chem, you'll have to learn 2 types. So type 1 is H plus a monatomic ion. And type 2 is composed of H plus a polyatomic ion that ends with 8. Sulfate, phosphate, bromate, etc. In Gen Chem, you'll learn about polyatomic ions ending in "ite," so that'll be your 3rd type, but we don't deal with polyatomic ions ending in "ite" in Intro Chem, so that's why you only have to learn these 2. So how do you name this type? You put hydro, and then you put whatever the monatomic ion's name is, and then you put the suffix ic acid. Hydro blank, and then ic acid. So for example, HBr comes from H plus and the bromide ion, right? So this would be hydrobromic acid, right? What would let's do H2S. What prefix will we use? Well, first of all, is that a monatomic ion that it's being paired with? Yes, it is, right? So this prefix would be hydro. What will we do with this sulfide? What does it become? Sulfuric acid, yes. I'm going to contrast that to plain old sulfuric acid in just a minute. What would HI be? Hydro, that's iodide, so what would it become? Iodide, you drop the "ide" and change it to ic acid, so that would be hydroiodic acid. Do we see how to do this? Now let's look at the other type. These are composed of hydrogen and a polyatomic ion ending with 8. So this is just blank ic acid. There's no hydro. Okay, so do you see the difference between the type 1s and the type 2s? When it's a monatomic ion, you put the hydro prefix. When it's a polyatomic ion that ends with 8, you drop that hydro and you just change the suffix to ic acid. So, for instance, let's do HNO3. Nitrate is a polyatomic ion. So what would the name of that be? Nitric acid, right? H2SO4. Now over here, we had hydrosulfuric acid. What's the name of this just going to be? Sulfuric acid, right? Because that's the sulfate ion. Okay, do we see how to do this? So I'm going to give you a couple to try, just for practice, and make sure we're good at this before we go any further. So I'm going to draw a little table on the board, name and formula, and you complete the table. Let's do pause it, let you try those. All right, let's go over these. What's the name of H3PO4? Phosphoric acid, right? Because that comes from phosphate ion. What's the formula for hydrofluoric acid? HF. That's hydrogen ion and fluoride ion, 1-to-1 ratio. What's the formula for carbonic acid? All right, H2CO3. Because carbonate is CO3 2 minus, hydrogen ion is H plus. And then what's the name of HCl? Hydrochloric acid. Do we feel good with naming and writing formulas for common acids? Now in intro chem, we're not going to worry about whether they're strong acids or weak acids. That's a general chem 2 topic. We don't even get into that in gen chem until gen chem 2. So we're not dealing with strong versus weak. We're just dealing with what's their name, what's their formula. Now for common bases, the nice thing about common bases named just like ionic compounds. Right, so that makes us happy. That's easy. No new rules to learn there. So for instance, LiOH, what's the name of that? That's just lithium hydroxide, right? The only one that you may not know off the top of your head, NH3, what's the name of that? Ammonia, good. Okay, so naming common bases is no worse than what you already know how to do. Okay, there's no new rules to learn for naming common bases. Woohoo! Now for common bases, some properties of common bases. They have a pH greater than 7. Okay, that's the range for common bases. They taste bitter. So think about cocoa beans, like if you actually go home and just take a scoop of like cocoa powder, right? It tastes kind of bitter. Coffee tastes kind of bitter, right? It's basic. They also feel slippery. If you're ever, spraying down your sink in your kitchen to clean it and you're using a basic cleaner, you get it on your hands, it feels kind of slimy and slippery. That's the property of the common base. All right, so those are some general physical properties of common bases. Everybody good on common bases? No new rules to learn there. All right, so let's talk about acid-base neutralization. And this is a net ionic equation. Acid-base neutralization. So the generic equation is acid plus base produces water plus salt. Acid and base produce water and salt. So let's do an example. Let's do HBr as our acid and LiOH as our base. Let's talk about, and these would both be AQ. Let's talk about where the water is going to come from. The H of the acid, OH of the base. Look, it's just a double displacement reaction, right? Because this is the cation, this is the anion. They're getting together. What's HOH the same thing as? Right, that's just H2O. And that phase is liquid. And now, double displacement again. Cation getting together with the anion, cation get together with the anion. So what's our salt? Lithium bromide, right? And you can look it up, but it is aqueous. So it's just regular old double displacement reaction. The net ionic equation for this would be H plus OH minus makes H2O. These two would cancel out, they'd be your spectators. So if you did want to write a net ionic equation for any acid and a base, the net ionic equation would just be H plus OH minus producing H2O liquid. Right? Because this would cancel out, they'd be your spectators. So it's just a regular old double displacement, and then they're all going to have the same net ionic equation. Always. That's easy. So I'm going to give you a couple to try. This one worked out that it was already balanced for us. We didn't have to balance it. So before you go any further, you don't have to write the net ionic equation because it's the same every time. But write a balanced molecular equation. I'll give you a couple to try. Let's do sulfuric acid and sodium hydroxide. And let's do how about hydrobromic acid and sodium hydroxide as well. Same base, just two different acids. So take a second and try those two. I'll pause the recording. Okay, let's go over these two. What's the formula for sulfuric acid? H2SO4. And what's sodium hydroxide? NaOH. So what are we going to produce? Water, it's a liquid, and what else? Good. Na2SO4. Is this one balanced already? No, we've got to balance this one. So what do we need?
1, 2, 2, 1.
All right, you need a coefficient of 2 in front of water and in front of the sodium hydroxide. The net ionic equation, which I wouldn't ask you to write, but just so you know what it would be, what would it be? It would just be H2, well, excuse me, H2. It would be H plus OH minus producing H2O. Okay. What's the formula for hydrobromic acid? HBr. And sodium hydroxide is still NaOH. That part hasn't changed. What are we going to form? We're still forming water. That's still a liquid, not aqueous. And our other product would be what? NaBr. Is this one already balanced? Yes. No balancing required here. Do we see how to write neutralization reactions? Do you want to do any more for practice, or do you feel okay with this? If you want some practice, there are lots of practice problems on this on the course website. If you go to, what week are we in? Week 12. If you go to week 12 and then click the practice section, there are a whole bunch of practice problems on this with the answer key. So if you want more, they're just ones that I made up and put up there for you. All right, let's talk about the pH scale, which is something you've probably heard of before, other classes. So let's talk about pH scale. But before we get into that, we need to talk about some symbols that you need to know. Anytime you see brackets, anytime you see these, that stands for concentration in moles per liter. So in other words, molarity. Okay, so anytime you see brackets around something, that stands for concentration, molar concentration. For example, if I said concentration of HCl, that would stand equals, I don't know, 2.0. How would that translate? That would mean the concentration of HCl is 2.0 molar. Okay? Do you see what that stands for? Little brackets. We're going to be using that bracket notation today. I don't know why my camera keeps going out of focus. You can still read it, though. I guess that's all that matters. All right. So, maybe if I erase the board better. It's like it's trying to focus on things that are not important. So the pH scale is based on concentration of H3O+. That's called the hydronium ion. So the net ionic equation for forming water, right, is H plus OH minus produces H2O liquid. Well, this H plus ion doesn't really exist in the real world, okay? It's actually H3O plus. Since we're in intro chem, we're not going to get obsessive about that detail, but we're still going to use the correct notation in our pH calculation. So just so you know where that comes from, okay, the hydronium ion is used because this actually doesn't exist. H plus is just a proton, and you don't have a proton just floating around. It actually combines with another water molecule and forms hydronium ion. All right, so that's where this comes from. So the pH scale is based on the amount of hydronium ion in your solution. Okay, and the pH scale is logarithmic, which means you have to use the logarithm button on your calculator. So don't let that scare you. It sounds scarier than it really is. The definition, calculating pH, pH is equal to negative log of H3O plus. Okay, so you take the logarithm of it and then change the sign. That's why I put negative around it. So for example, the concentration of H3O plus is 0.50 molar. The pH would be what? So take your calculator. Now my calculator gets mad if you enter that negative sign. It does not like it. So if I say negative log, it says error. It gets mad. It does not like that. So I just take the logarithm and then change the sign because you're going to get a negative number anyway. A negative of a negative is a positive. All right, so on my calculator, I would say 0.5 and then I would hit log, which is, where's my log button? I just saw it a second ago. There you go, at the top. Don't hit ln, that's natural log. Okay, just hit log. I got 0.30, well, I actually got negative 0.30, but when you take negative of negative, you get positive. So I got 0.30. pH is unitless. Did you get the same answer I got? So here are a couple for you to try. H3O plus concentration, you give me the pH, just to make sure you can do it. Let's do 1.37 times 10 to the negative 3. Let's do 2.51. And let's do 0.095. Take a second and try those. All right, let's go over these. Now, to enter the times 10 to the negative third, what button do you use in your calculator, if you have it? The capital E, right? That enters that exponent for you. So if on my calculator, I say 1.37 E, and then I say negative 3, that enters that exponent for me. And then all I do is hit log. So I get negative 2.86, which I then change the sign. So that would be positive 2.86. Remember, pH is unitless. All right, 0.99 log. That gives me negative, which I then change the sign of. So it'd be 0.0044. 4.4 times 10 to the negative third. 0.095 log. 1.0. That's really it. All right, so what are all of these? Acids or bases? Are their pHs greater than 7 or less than 7? They're way less, right? This one's significantly less. So these would all be acids. If you have a pH that is greater than 7, what would that be? That would be a base. All right, so pH is just a negative log of H3O plus. Does that make sense? Let's go the other direction. What if I give you H3O plus and ask you to give me the pH? Does anyone know how you undo a logarithm? Can you think back to your algebra class? You're given, you're given pH and H3O plus concentration is unknown. Here's the relationship here. H3O plus is equal to 10 to the negative pH. And it needs units. Your units would be moles per liter. Okay, you have to have units here. So let's do some examples. The pH equals 12.2. H3O plus would just be 10 raised to the negative 12.2. So in my calculator, on my calculator, if I hit second log, there's a button that looks like 10 to the x. That's what mine looks like. Do you guys have a button that looks like that? So if you just say negative 12.2 and then hit 10 to the x, that enters it in for you. And so I got 6.31 times 10 to the negative 13th, and my units would be moles per liter. Now that's a really, really low number. Would you expect there to be a lot of H3O plus in a basic solution? No, right? Because basic, this is P. How did I know this was a base? How did I know it was basic? It's greater than 7, right? So that means this is a measure of acidity, right? That's coming from the acid. So if this is a basic solution, you would not expect there to be a whole lot of the acid component in there. So I'm going to give you a couple to try just to make sure you can do it. I give you pH, you give me hydronium concentration. So pH equals, let's do 0.044. Let's do pH equals 9.73. Let's do 7.00. And let's do 11.1. Pause the recording. All right, let's go over these. So to get hydronium ion concentration, this would be 10 to the negative 0.44. So 0.044 negative 10 to the x, 0.90 molar. All right, this one would be 10 to the negative 9.73. 9.73, 10 to the x. That gives me 1.86 times 10 to the negative 10th molar. 7, this would be 10 to the negative 7th. So what is that one? Oops. When you enter that into your calculator, you're just going to get what? 1, 2, 3, 4, 5, 6, 7, right? There's something special when pH is equal to 7. What do we call that? Neutral, right? This one's neutral. A neutral solution has pH of 7. Concentration of 1 times 10 to the negative 7th moles per liter. And then 10 to the negative 11.1. 11.1, 10 to the x. This would be 7.94 times 10 to the negative 12 moles per liter. All right, let's go through and classify these as acids or bases. What's this first one that we did? We already did that one. That one's base. What's the second one? That's very strongly acidic, right? What's the next one? Base. We know that this one's neutral because it's 7. What's this one? Base. And again, you can always know it's a base because its H3O plus concentration is going to be really, really low, right? Because remember, H3O plus is the acid component. And so you would expect that acid component to be really low in a basic solution. Now let's go the other direction. We know pH. There's another pH scale, well, P scale, it's not a pH scale, it's just a P scale. It's called pOH. Really doesn't erase well. I just need to get a new eraser. So let's go back to our net ionic equation for water, right? H3O plus OH minus produces H2O liquid. All right, this is the acid component. This is the base component. Right, so we use pH here, and we calculate concentration of H3O+, right? So in an acidic solution, the pH will be very low, the concentration of H3O+ will be very high, right, if it's an acidic solution. The base component can also be measured. So the pH scale is based on the concentration of the acid component. There's also a way we can measure this. It's called the pOH. And we calculate the concentration of OH minus. Okay, so that's where these two scales come from. Maybe you've heard of the pOH scale before. Maybe you haven't. Maybe this is the first time you're hearing about it. The pH scale is measuring the acid component. The pOH scale is measuring the base component. So if it's an acidic solution is high concentration of H3O+, right? A basic solution would have what? Right, it would have a low H3O+, but it would have a high OH minus. So you see these two are opposite each other. They're like two directions of a highway, right? One's going this way, one's going this way. Because the pH scale is 0 to 14, and here's 7, that's neutral. So 0 to 7 on the pH scale would be acid. 14 to 7 would be base. These two are the opposite of each other. So if you're going the other direction, 0, 7, 14. Here would be your acid section. This would be neutral. And this would be your base region. Do you see how these are the opposite of each other? They run opposite directions. If you have a high pH, you're going to have a low pOH. And if you have a low pH, you're going to have a high pOH. They're opposite directions of each other. 7's neutral on both of the scales, though. If you understand pH calculations, pOH calculations work exactly the same way in your calculator. Exactly. So let's talk about pOH calculations. If pH was calculated as concentration of H3O+, what do you think pOH would be? pOH is negative log of OH minus. Because that's what the pOH scale is based on. Right? Does everyone see how to translate this from pH? So for example, concentration of hydroxide ion is, let's say, 1.93 times 10 to the negative second moles per liter. What's the pOH? Well, you just do it in your calculator. 1.93 times 10 to the negative 2. Take the log of that, and then change the sign. You get 1.71. Now on the pH scale, we classify that as an acid. But the pOH scale is the opposite. Right? What will we classify this on the pOH scale? Base. This is a base, right? Because if it's low on the acid side, that means it's high on the base side. So let me give you a couple to try, and then you classify them as acids, bases, or neutral. So let's do, am I still in the frame here? Yep. OH minus equals, let's do 4.6 times 10 to the negative fourth and 0.082. And that's enough. I think you guys have the hang of this. I'll pause the recording. All right, let's go over these two. Calculator. 4.6 times 10 to the negative fourth. Take the negative log of that. Did you get 3.33? Get that? Is that an acid or a base? That's the POH though, careful. Be a base, right? And 0.082, take the log of that. And we change the sign. 1.09. Again, what would that be? That would also be a base. Right? If it's low on the POH scale, it translates to being high on the pH scale. Now let's talk about how you'd go the other direction. It works just the same as it does. That works a lot better. Maybe. It's showing up on the screen. Okay, so let's go to the other direction. If OH minus concentration, if POH is given, concentration of of OH minus is just 10 to the negative OH minus POH, excuse me. So for example, POH is equal to 0.95. Concentration of hydroxide ion is just 10 to the negative 0.95. So in your calculator, 0.95 negative 10 to the x. So that would be 0.11 moles per liter. And again, don't forget units. Concentration is in units. pH and POH are unitless. So if POH is equal to 2.3 times 10 to the negative 10th, what is hydroxide ion concentration? I'm not going to list a whole bunch of them on your board. Let's just try this one. 2.3, 10 to the negative 10th. Did you get 1 times 10? Hold on. 2.3, 10 to the x. Did you get 1? Did I do something wrong there? I guess it's really, really darn close to being 1. 2.3 e 10. Get the same answer I got? I got 1. 1. Okay. Yeah, mine's carrying out a whole bunch of zeros and then a 1. We'll just carry it like that. Moles per liter. All right, do we see how to do this one? It works the same way as going between pH and POH. Now, this is a really important conversion factor that'll make your life super easy. Because if you know one value, you can calculate all the other ones. So this one is, I put it in special color in your notes. pH plus POH is 14.00. Ooh. I don't know if that showed up on the camera. Nope, not really. That's okay, it's important enough to go over it again. pH plus POH equals 14. And now if you know one, you know all the others. So I'm going to give you, I'm not even going to go over examples on this. I'm just going to put one up on the board and see if you can figure out all the other ones. Because I feel like I'm kind of repeating the same thing over and over and over. Sure, it probably feels like that for you too. So here, this is what you're given. pH is equal to 2.3. I want to know H3O plus. I want to know POH. And I want to know concentration of hydroxide ion. Because if you know that one piece of information, you can calculate all the others. Let's go over how we do this. H3O plus, what calculation do you do? 10 to the negative 2.3, right? So in your calculator, 2.3 negative 10 to the x, that would be 0.0050. Does H3O plus concentration need units or is it unitless? It needs units. What are those units? Moles per liter, capital M. How do I get POH? pH plus POH equals what? 14. So how do I get POH? It would just be 14 minus 2.3. So what'd you get? When you subtract that out, what do you get? 11.7. And does that need units? Do pH and POH need units? No, they don't. They're unitless. And then how would I get hydroxide ion concentration? That would be 10 to the negative POH, which we just found. So 10 to the negative 11.7. So 11.7 10 to the x. 1.9, actually that'd be 2.0. It's 1.995. So let's go with 2.0 times 10 to the negative 12 moles per liter. Based on this data, is this an acid solution or a base solution? pH 2.3. Based on this data, this would be an acid, right? Do you want to try one more where I give you one and you figure out the other three? Or have you got the hang of it? I'll try one more just for good measure. All right, let's try one more just for practice. I'll give you a different thing this time. All right, this time I'm going to give you hydroxide ion concentration is equal to 0.0035 moles per liter. I want to know, and you can do these in any order you want, pH, POH, concentration of hydronium. Because if you know one, you can solve for all the others. All right, last one. Let's go over this one. So I gave you hydroxide ion concentration. Can that be useful in calculating pH? Can I go directly from this to pH? I have to do something else first. What do I need to do first? Because hydroxide ion doesn't give me enough information to get pH, does it? What do I need to calculate first? Can't calculate pH from an hydroxide. What do I use? Calculate POH, right? Can I calculate POH? Yeah. So that's negative log of 0.0035. So 0.0035 log, that would be 2.46. Now can I get pH? How do I get pH? Right, 14 minus 2.46. So what's that? What do you get when you do that subtraction? What? Okay. And then how do I get H3O plus? 10 to the negative pH or POH? pH, right? So 10 to the negative 11.54. I got 2.88 times 10 to the negative 12. And that needs units, that's moles per liter. Based on this information, is this an acid or a base?
Base.
This one would be base. High pH, low POH, low concentration of the acid component. Do you see how to do these problems? You figure out one, and then all the other ones fall into place. Make sense? Makes sense. Okay, that's where we're going to stop for today.